get started.
Okay.
So welcome everyone to present here on my final PhD Thesis Defense. And the topic I'm going to talk about will be the phase change heat transfer and the enhancement of cryogenic chill down process. I pick up the two most interesting parts. I'm doing one is experimental, one is molecular dynamics. So the presentation is going to divide into 5 parts. So first one I'm going to talk about something on the motivation, like why I'm doing that, and second one will be a literature review, which I go over 3 different literature, very similar to our work. And then I will talk about a method which I use for a long time, is the data analysis part. And also I will talk about the 2 specific projects. One is nanosurface quenching and heating boiling. Another one is the molecular dynamics simulation of a droplet on a plane surface. MD here refers to molecular dynamics. I take it first 2 numbers. So first one, we're going to talk about something on the motivation, why I'm doing that. So this boiling curve, I think everybody here is very familiar with it. We have so-called forward and backward. The forward boiling, we start from A, which is the onset of a nucleate, from A to B, and then jump direct to D, from the critical deflux to the film boiling. But for the quenching, it's different. We start from D, goes through C and B, and finally will be A. So that we call the backward, or we call that quenching process. Please remember this curve. Remember this curve is really essential to this presentation. And second one, I will pick up 3 very interesting literatures. First one is somebody doing a nanoparticle surface quenching. Actually, it's not a nanoparticle surface. It's just a plain surface with a nanoparticle fluids. But when you finish the quenching, there's a lot of particles going to deposit on the surface, so they will create the so-called nanoparticle surface. And they found they will increase the lantern fracture point like around nearly 100K for the water. It's a very big improvement. But when you repeat the experiment for several times, there's more particles deposit on the surface. The small cavities for the bubbles will decrease. So the effect of number of particles is decreasing. And second one, which was done by a Korean group of people, that was last year, 2 years ago, 2013. They created a nanoporous surface. They use the same substrate as us and a similar method. And instead of quenching, they do the heating. And also you can find here, on the right hand side, there's 2 SEM here. You will find not a very perfect honeycombs, but small holes aligned with each other on the surface. They will provide like a nuclear site. And when you look at the right hand side, you will see 2 figures, which demonstrate this. When you have a lot of experiment, repeat, the effect is getting worse and worse. And also when you look at here, this figure will show you the difference between plane surface and the nanoporous surface. I would say it didn't seem to be a lot of difference actually. And also the analysis is given out, they just say it provides a porous cavities provides the nuclear site, but they didn't really go very deep into it.
Is the red and the blue referring to different surfaces or just different experimental runs?
Okay, this is basically 2 different surfaces,
Yeah.
and in each of figure, the different color refers to different runs,
Okay.
different tests. So they do a repeating test.
Got it.
Different time, actually.
Okay, different time.
And this one was done by Berkeley, and they create nano wires on the surface, and between the nano wires, there's a small cavity inside. So they also function like a nucleoside. But first one, they're using the silicons, and everybody knows silicons is really bad on the stress. If you provide it with suddenly a huge amount of energy, they'll crack easily. And also the nano wires, silicon nano wire doesn't show much improvement. For some specifications, when you look at it here, you will see either these purple ones is a plain silicon surface. There's no nano wires. but with different lengths, you will find the little length, like 16 millimeter or 16 microns, will do the best job. But when you have it longer, it doesn't actually improve, but actually decrease the efficiency. So all of the nano wires create a surface like a thermal barrier actually. When you have it too long, too much, and too dense, they have a lot of vapor inside. They try to store the vapor inside and prevent the bubble to create. So that's actually function like a thermal barrier. That's not something we want. That's bad. So based on all of these things, we try to do something different. And I was talking about the data analysis here. I think everybody have already seen this equation before in my proposal defense, and also my algorithm on this one with the self-adaptive parameters. So I will skip this part. And then we're talking about the experiment on nanoporous. So several questions we want to answer in this experiment. First one is we want to know the thermal hysteresis. So-called hysteresis is for one surface if it's different from the quenching and the heating. Because although they all called boiling, forward and backward, will they be the same on the same surface, on the same condition. And second one is there's somebody I have used the pure aluminum, which is I refer to AAO. It's a pure aluminum, 99.99% of pure aluminum surface, which is very soft and it's actually not good for engineering application. But now I've shifted to 1661 aluminum alloy, which you use a lot in the submarines, airplanes, and even the linear accelerator. So that have a better engineering application. And third one is how to compare the critical heat flux and the London Frost point, which is very critical parameter on the backward boiling, or referred to quenching. How that will be different from the normal surface and the nanoporous surface. And also the critical heat flux on these two different surfaces during the heating, just like the going forward, from the signal phase and create a bubble. How that one going to be different. And the final will say why, and we want to answer the question why it's different on the nano surface and the plane surface. So this is my experiment test operator setting up. The left-hand side will be a 3D model. You can see from here. It's very simple, but it's useful. I have a transparent vacuum liquid nitrogen small dewar, which is here. It allows me to take videos. And also we got a deck. Inside the deck we have a temperature thermocouple and a heating element, which is installed inside in the deck. And also we have laptop, the background light, which is used for my high-speed camera. And I have two different experiments. Which the first one, A, referred to here, will be first generation. There's no heating element inside. And for the figure B, I put the heating element inside. And for the heating element, I can change its power. I can change its time freely. No matter what, how big they are, how small they are, and what's the time stamp for each temperature. It's all controllable. And for the surface, I separated into two categories. First one is 6061 aluminum alloy, which I'm using right now, and another one is 99.99 aluminum, pure aluminum. We use the same method to create a nanoporous on the surface, and because in the 6061 they only have about 95.85% of aluminum. Others will be different metal elements like carbon, like silicon inside. So the nanoporous, the structure you will see will be different. Okay, like here, this one will be the normal surface with normal machine grounded, and the B here which I refer to PO15. 15 minutes. 15 refer to 15 minutes, which is the hole size opening time. So you will see the hole is kind of small, but it will have a lot of hole here. The number density is high. And this one is referred to PO 45. 45 also the time, hole opening time. With more time I open the hole, the bigger hole you're going to be, but the number density will decreasing. And for the right hand side, there are two figures. The first one is I use 30 minutes, pure 30, 30 minutes, which is the hole is very good aligned with each other and almost have the same diameter, which is about 50 nanos, and the depth is 5 microns. But for the lumen alloy, all of them depth is about 2 microns. So please remember these parameters, and we're gonna see that one later. Okay, here is the contact angle measurement. For the left hand side, it's 60, 61 lumen alloy. This is the normal, which means the normal machine grounded. And the B is PO415 and C is PO45. C with the increasement of the pore sizes, so you can have a very, very tiny contact angle. This one nearly to 0, and it's very hard to measure. So I use the MATLAB to write the code myself because equipment cannot really measure it. And for B and for A and B here, this one is a normal. It's about 74. And this one is the PO30, which is 30 minutes. So that one is about 13.1. So this is the surface characterization. So because we have different metal elements in the 61 alloy, so the pore size is different. You already see that with the SEM. Then we want to know, okay, how actually the size looks like. Because that's no longer a single value, it's a distribution. So I take the picture of a SEM on 3 different locations, and then I use the MATLAB to take the picture out of it and try to find its boundary. When I find the boundary, the black ones will refer to the hole, the lighter ones, like the gray, will refer to the surface. And then I can say, okay, I can catch the surface. I can catch the holes. I can catch each of the holes. I can catch each of the holes, the size of the holes. And then I will put them together to create a histogram. When you have a histogram, then it will be easy to fit it with a distribution. And this, I use a wearable distribution, which is used a lot for the environmental protection area in the environmental engineering, which they try to analyze the seed size or the ash size, which is very similar to what we are using on the same order, micron order, nano order. So I use the distribution provided with them, and with a linear trust zone algorithm, which basically an iteration. We try to find the minimum mean square error. Then we have 2 distributions, PO15 and PO45. And we can see that for PO15, which most of the size, it will be very tiny compared to PO45. It's around 0.01 microns, but the PO45 is on 0.025 or 0.030 microns. So this parameter will be very important, and then we will see that one again. This is a crunching curve we got on the 99.99 aluminum alloy surface, which I was done last year. What we can find here is the nano surface actually works, and a very important thing is they pump the London frost point around 30 Kelvin. It's a lot, from about 120K to about 150K. It's a lot, and also they gave us about 3 times higher critical heat flux. And also we saw so-called 2-stage crunching, which you can see here. This part will be the transition boiling region, but we saw that 2 part. It's got 2 different lines here with a different K probably. So actually that indicates there's 2 different mechanisms behind it. And then we will have a better analysis on that, and so because somebody has suggested this, the transition boiling actually is a combination of film boiling and the nucleate boiling. some surface will cover the film, some surface is still on the nuclear side. So then that's a combination. So we divide these two into two different parts, which this part will be more film dominance, but another part will be more nuclear dominance. And here is the picture I took on the experiment. So the top two will be the normal surface, and bottom is non-droplet. So we can see here, the most different part will be here. Actually, the nucleation boiling part. You can see the bubble here is kind of smaller, and there's not a lot of bubbles try to climb with each other. But when you see the normal surface, you see huge big bubbles, and there's bubbles try to climb with each other. When you have more bubbles try to climb to each other to create a kind of a vapor, so that's actually decrease the heat transfer coefficient. But if you have a huge amount of small bubbles, that's something we want. And now we talking about, let's see, that one was the quenching on the 99.99 pure aluminum surface. And now we want to see how the quenching and heating is different. Because we have seen there's already two regimes on the on the heating, on the quenching in the transition boiling regime, which is H2I and G2H. So there's already two parts. And then we want to see if there's another two parts, possibly. If there's another two parts in the heating with the same structure, but actually we didn't find it. So this was done by several weeks ago. It's on the 6061 aluminum alloy. So we can see this is the experiments. The data acquisition was improved, and the control program have been improved. They will give me a better measurement actually. So we can see here, the film boiling regime is perfect overlap with each other. So that means maybe the film boiling regimes with